Hello, everyone. I'm Sagar Bharadwaj from Carnegie Mellon University, and I'll be talking about a system called OpenFLAME, which is a federated spatial naming infrastructure. Let's say there are autonomous robots that have to deliver food from restaurants to their customers outside the city. And in this instance, it has to deliver food from a restaurant called Ghost Kitchen in Pittsburgh downtown to my office in Carnegie Mellon. It would be nice if this robot had access to a map that can help it navigate from the ghost kitchen to my office. And of course, there are already maps today. But today's maps, like Google Maps and Apple Maps, etc., answer only a part of the problem. For example, in this case, they know where Ghost Kitchen is and where Carnegie Mellon is, but they do not know where the pickup area is within the Ghost Kitchen or where my office is within Carnegie Mellon. A ubiquitous map, or a map that spans across indoors and outdoors, would make the robot much more efficient in its navigation task. So why are maps today not ubiquitous? Because first of all, indoor data collection is hard. It requires huge manual cartography effort. And to make things worse, many indoor spaces are private and also highly dynamic. Now you might say crowdsourcing is a solution to all of these problems, and you would be right. Crowdsourcing does increase coverage of maps, but crowdsourcing on a central system is not the right way to scale because businesses do not want to expose their indoor map data due to privacy and competition concerns. Autonomous robots was just one example, but spatial applications are a wide range of applications ranging from inventory management, facilities management, augmented reality, and so on. In fact, we think that the next generation of the web is going to be the spatial web that is going to host all of these applications. And as part of the systems community, we think that we have to start building the infrastructure to enable this next generation of the web. Our solution to this infrastructure is federation of maps, or an infrastructure that allows independent organizations to maintain their own maps of their own spaces. So, for example, on this street, each of these different buildings would have their own maps. Target building here would have its own map hosted on targetmaps.com, for example. CMU would have its own map, and so on. Public spaces like roads would continue to be maintained by organizations of today, like Google. This looks just like the web of today, where different organizations participate independently in the system. But the web has the DNS that associates names like google.com with servers. Similarly, for the physical world, we need an infrastructure that associates regions with their map servers. And that's what OpenFlame aims to be, the DNS for physical spaces. OpenFlame provides the discovery mechanism to identify maps at the current location, and also a protocol to talk to maps and get services from them. The fundamental unit of OpenFlame is what we call a map server. A map server is a system that stores the map data of a region and also provides services on the map, such as search and routing. These map servers are maintained by independent organizations. There's also an OpenFlame client that is running on the device alongside applications that discovers relevant map servers and obtains services from them. Map servers that are administered by a single organization is grouped under what we call a map zone, and this is for administrative convenience. When we think of administering spaces in the real world, there is always a lot of delegation involved. So, for example, there are countries, states, counties, and so on. Similarly, we think that incorporating delegation chains in our system would make the growth of the system much more natural. Let us look at examples of map zones and map servers that could be hosted on CMU campus and how they could be organized. So there's the global zone or the root zone, and just below the global zone, there could be Apple and Google zones that have world maps. The CMU zone itself would be under the city zone, which itself would be under the US zone. CMU zone could have maps like CS department map, maths department map, and so on. In addition to all of this, there could be a CMU pipeline map that is maintained by the Waterworks department uh, under the city zone. A device within the CS department map, for example, when it launches a discovery query to discover maps, OpenFlame would return all of these maps across all of these zones, Google Maps, CS department map, CMU pipeline map, etc. A consequence of allowing map zone overlap is that these branches are not exclusive, unlike in the real world. So, for example, if CMU quarrels with the city zone, and city evicts it from its zone, CMU can always set up its own zone and register itself under the US zone directly, for example. And OpenFlame would still discover CMU zone as if nothing changed. Now, DNS is structurally very similar to OpenFlame. It has similar concepts of delegation and hierarchy, etc. And as a result, we implement our map zones as DNS zones, and we implement pointers to map servers as DNS records. The advantage of doing that is that it immediately unlocks this world-scale DNS deployment that already exists, including its ubiquitous caching mechanisms and CDNs, etc. And this allows us to bootstrap the system without building a whole new infrastructure from scratch. So let us look at all of this working in practice. So this is a map visualization application that is built on top of OpenFlame. The sidebar on the right shows the list of maps that are discovered in the current view. Google Maps is already discovered because it has coverage over the entire world. So now if I zoom into a building on CMU, we see that it discovers many maps that are specific to CMU. And if I reduce the opacity of Google Maps, we can see the inside of CMU building. And these maps are all streamed from CMU map servers that are hosted within the campus. And if I go to a different part of the campus, we see that a different set of maps are discovered. The advantage of federation is that these organizations can implement their own access control mechanisms. So for example, let me go to the incognito mode here and let me open the same map. Now, if I zoom into one of CMU's buildings, we see that CMU map server is still discovered, but we cannot see the CMU maps because we haven't authenticated with the map server yet. And only individuals with cmu.edu address can see CMU maps, for example. So how is OpenFlame discovering all of these maps within the user's view region in this application? Let's say this is the virtual camera through which the user is seeing the map. And the green polygon here is the search polygon, or this is the area within which maps have to be discovered. So OpenFlame first converts this search region into a list of domains, what we call geodomains, and these domains represent this region collectively. And a discovery query on OpenFlame involves just launching all of these DNS requests in parallel. And these DNS requests can be served by existing DNS servers without any changes because we do not make any changes to the DNS query protocol. What are these geodomains? We built geodomains on an existing spatial indexing system called S2. So S2 divides the world into hierarchically organized square cells. What I'm showing here is the top level of the hierarchy, and we have labeled them 0.lock and 1.lock. As we go down the hierarchy, the size of these S2 cells becomes smaller and smaller, and we can assign geodomains to each of these S2 cells. Registering a map on OpenFlame involves generating a DNS zone file that represents the map region. So let us look at an example of registering a DNS zone file for CMU. So we have a tool that can automate the process of such registrations. So we can draw a boundary around the region of the map that we want to register. And this boundary can be rough because OpenFlame accommodates fuzzy boundaries. And then we can generate cells, S2 cells that cover this region, and then enter all of the information that is required for generating these DNS records. So, for example, uh, the suffix and the type of the record, etc. And once we hit generate zone file, it generates a DNS zone file that can be directly hosted on any existing map server, sorry, any existing DNS server. We've also implemented some location-based services on top of OpenFlame. So for example, this is the search service that is implemented as part of the map visualization application. And this searches for the user input strings across all the discovered maps. So for example, here, we see that when CMU is searched, there's a result from Google Maps for CMU. And when that is selected, it zooms out into onto to show the whole CMU campus. And next, when the user searches for gates, which is a building that is within CMU, we see that the result from Google Maps is not very relevant, but then the result from maps that are hosted at CMU are more relevant because it shows all of the places specific to CMU campus. So when one of this is selected, it takes us inside the building and shows us Gates Lounge, for example. And this is another result showing Arena Lab, which is a lab that I'm part of at CMU. And this is an example of routing. So this is routing implemented within an individual map. So this is routing within the CMU map. And this is routing inside a different map, which has most of Pittsburgh City, except the campuses of Carnegie Mellon and the campus of University of Pittsburgh. But this map still knows how to reach from one campus to the other, but it does not know the internals of each of these campuses. So combining these two maps gives us more accurate navigation or routing results to take us from one campus to the other. This is an augmented reality application that is built on top of OpenFlame using its localization service. And of course, there's much more in the paper. For example, we talk about security, how to confirm the identity of a map server. We also show if some preliminary results for if this is feasible or not, and does this significantly increase the load on DNS. We also talk about how DNS records can handle overlaps in discovery. I would also encourage you to go to our website, open-flame.com, because this project is much more than just this paper. Thank you.